welcome back everyone. We are in section 3.3 talking about applications of the derivative. We're looking at optimization. So the goal with optimization is to maximize or minimize a particular quantity in a modeling problem. So we're applying the same techniques that we've been working with the last couple of sections, but just applying them to specific contexts. So in this section, we're not really learning anything new necessarily, but we're seeing how we can apply techniques we've already learned. So when we want to optimize a value, our general strategy follows these basic steps. So draw a figure when appropriate. So if there's a case where you can visualize it like graphically or using a diagram, that's always a good idea. Every little bit of extra information that we can get helps simplify the problem. We're going to assign variables, so give everything a label. Select the quantity to be optimized, and construct a function to relate the variables. So we need to ask ourselves, what are we optimizing in any given question? And then we need to create some sort of relationship, right? Some sort of function that we can then find the max or the min. We need to eliminate any extra variables, and that will allow us to differentiate. Okay, and that gives us our critical values, and then we can then test for the absolute extrema. So let's take a look at our first example here. A rectangular region along the bank of a straight section of a river is to be enclosed with 80 feet of fencing. Only 3 sides need to be fenced since the river will bound the other side. What are the dimensions that will produce the greatest enclosed area? Okay, so let's look at what we know. We know we have a rectangular region and it is enclosed with 80 feet of fencing on 3 sides. Okay, and then it's asking, so what is it asking for? It's asking what are the dimensions? So it's asking us to find the dimensions of this rectangle that produce the greatest enclosed area. Okay. Now, greatest is one of those words we need to keep an eye out for because that is basically just a synonym for the term maximum. Okay. So we know that the amount of fencing around these 3 sides is 80 feet. And we know that we are trying to find the dimensions that maximize the area in here. Okay, so we have area. In terms of our side lengths, you can call them whatever you want. I called them width and length, so like L and W. That would be another width over there. Okay, so I have my diagram. I have some variables set up. Now we want to set up the equations. So the first one, we're going to work with the sides. So we can talk perimeter. So the perimeter of this, remember, we're not using the 3rd side over here because that's a river. So no fencing is built over there. But the other sides, this W, and this L, so 2W plus L, add up to 80 feet of fencing. And then there's the function that we're trying to optimize. We want to find the formula for area, which in a rectangle like this is just length times width. This is the one we want to work with, but we need to get rid of the extra variable. We can only work with one variable at a time. So we're going to use this one and solve for either of the variables. I'm going to solve for L. because then I don't have to divide by 2. Don't get a fraction in there. Right. I'm going to replace L in this formula with this. So this is going to give us a function a of w equals 80 minus 2w times w. So again, if we go back and look at our steps here, draw a figure, we did assign variables, we did select the quantity to be optimized, we did construct a function to relate the variables, we did. So this relates the variables with that constant 80. This function is the one that we're going to optimize. We eliminated any extra variables, right? Now there's only one. And now we get to step 5, which is where we differentiate. So we're going to, let me go ahead and distribute this first before we take any derivatives. So that's 80w minus 2w squared. And now we can go ahead and take the derivative. So that'll be a prime of w. So that's 80 minus 4w. We set that equal to 0. We get 4w equals 80. So w equals 20. Now, before we draw any conclusions, we do need to verify that this value of w does produce a maximum. So if we set up using a number line, put 20 on here, check a value to the left, like 0, we get a positive. So that would be like a of 0. Sorry, that's kind of messy. A of 0 is positive. If you pick a value like 30, you would get 80 minus 120, which is negative. So we go increasing to decreasing. So it does produce a maximum. Okay, we don't want to assume that this produces a maximum because when we're talking about finding the extrema in these cases, we're looking for absolute extrema, which could potentially include endpoints. We're not going to see that case here because the endpoints would force one of the side lengths to essentially become 0 in order for that to work. But hypothetically, if this had been a minimum, then the maximum would be at one of those 2 endpoints. So we need to check just to rule that out as a possibility. So we do get a maximum. Okay. Once we have W, now we get L. So L was 80 minus 2W. So L is 80 minus 2 times 20. 80 minus 40 is 40. Right. So this asked for what are the dimensions that will produce the greatest enclosed area. So those dimensions are 20 by 40, right? So a 20-foot by 40-foot region will maximize the area. Now you have to be very careful when answering these types of questions to always make sure you actually answered what the question asked for. In this case, it asked what are the dimensions. So that's good. You can get cases like, for example, if this had asked what is the maximum area, then we would just need to do a side, like an extra bit of work here. Note the max area is A of 20 So we plug in the W. So that's 80 times 20 minus 2 times 20 squared. That's 800 square feet. And again, this question in particular did not ask for that. But if it had, there's plenty of times where students will get the 20 and the 40, box those up as a final answer and say, we're all done. And then they don't go back and read and say, oh, the question actually asked, what is the maximum volume? Or it could ask for both. So always with these types of optimization problems, go back to the beginning and make sure that you actually answered the question. And because these questions are given in context with like words, you do want to write your final solution in words. It doesn't have to be a paragraph or anything, just one sentence, just to, in words and in context with units, explain what your answer is to the question. So let's take a look at the example at the top of the next page. The concentration C of a drug in the bloodstream T hours after it has been administered is approximated in milligrams per cubic centimeter by this formula C of T, where T is non-negative. When is the concentration the greatest? When is the concentration the greatest? Okay, so we have a formula. It's asking when. So it's asking for a T value. And it's saying when is concentration the greatest? So it's asking for when C of T is maximized. Okay, so being able to read these statements and interpret them is very important to be able to answer these types of questions. So we're going to start off like we do with pretty much everything in this chapter. If you ever get a question like one of these, good rule of thumb, when in doubt, just take a derivative. That's usually a pretty good way to start. It's not, every problem that starts that way, but a lot of times, that's our main focus in a lot of this class. So let's take the derivative of this. So we're going to take the quotient rule. So we're going to get low d high minus high d low all over low squared. And that's not particularly nice, but it does simplify down a little bit. So this whittles down to negative 14t cubed plus 126 over t cubed plus 18 quantity squared. So if we take a look at that numerator, so we set this equal to 0. So the numerator is the important part, because if the value doesn't exist from the denominator, that's not going to help us. So we get negative 14t cubed plus 126 equals 0. This one is actually divisible by 14, or by negative 14 if you like. So that would give us t cubed minus 9 equals 0. That gives us t is the cube root of 9. Be very careful. Cube root of 9 is not 3. That would be the square root of 9. Cube root of 9 is not a whole number. It's irrational. It's not something that we can get exactly. We would have to approximate using like a calculator or something like that. So we can just leave it like that for now. We do need to verify that it's a maximum, because that's what the problem asked for. Okay, cube root of 9 is a little bit more than the cube root of 8, which is 2. So we could pick 2 down here and then pick like 3 up here. But if we do that, so if I picked 2, for example, this will always be positive. And then if I pick 2, you get negative 14 times 8. And then plus the 126 6. So that still works out to a positive. And if I pick a bigger number than this, that becomes larger. So that gives us the negative. So we go increasing to decreasing. It is a maximum. And so the question was when, right? The t value. And so we can say maximum concentration occurs after cube root of 9, which if you want to answer in context, we can go ahead and use a calculator and just get, it's about 2.08 hours. So the maximum concentration in the bloodstream occurs after a little more than 2 hours, according to this formula. Right. Let's take a look at another example with a little bit more going on in this one. We've got a little bit more setup to do. So an online business wants to know how to price their inventory in order to maximize profit. Currently, they sell 20 items a week for $400 each. That costs the store $200 each. They estimate that for each $10 reduction in price, they can sell 2 more items each week. Find the price of each item that will produce the maximum profit for the business. So we're looking to find the price of each item. That's ultimately what our goal is. And that price should be the one that maximizes profit. So in order for us to get profit, we need a profit formula. We are not given a profit formula. We are just given information, right? Data, numbers, and we have to construct this formula. We're going to need some variables here. So let's see, what do we have here? We have number of items sold per week, right? We have their charging price, the cost of those items, and then they work with $10 reductions in price to get 2 more items each week. Okay, so I'm going to use X to represent the number of items sold. And then I'm going to use R to be the number of price reductions. Now, if we want to get profit, remember profit is revenue minus cost. So it's the amount coming in that you're making minus the amount of money going out that you're spending. So we're going to need revenue. So revenue, that's going to be R equals price times quantity. So in terms of the quantity, that's X. In terms of the price, it's going to be 400 minus however many reductions they do times $10. So let me get this written in here. So 400 minus 10R times X. So this is revenue, this is price times quantity. So again, they charge $400, and then if they want to reduce the price, they take 1 reduction times $10, or 2 times $10, or 3 or 4 or 5, however many, and that lowers the price. And then times X, which is the number of items that they sell. Now, X, this number of items, can also depend on the number of reductions. remember that currently they sell 20 items a week. And every time they reduce the price, they can sell 2 more items. So we have 400 minus 10R. X, the quantity that they sell, it would be 20 plus every time they reduce the price, they sell 2 more. So that's 2 times the number of reductions. Okay. So this is our revenue function. So that's going to be 8,000 plus 800R minus 200R, so plus 600R minus 20R squared. That's our revenue formula. Cost will be C. Cost is going to be $400. Let's see, no, they sell them for $400. They cost the store $200 each, right? So 200 times however many items they sell. And then this formula, we can also put it in terms of R, just like we did the last one. So 200 times 20 plus 2R. Okay, so C, if I multiply that out, that's going to be 4,000 plus 400R. So as you can see, the setup on a problem like this is a huge part, because we haven't even gotten to the profit formula yet, let alone do the calculus on it. So for the profit formula, that's going to be P. That's revenue minus cost. So we take this formula minus this one. So that's going to be 8,000 minus 4,000, 600R minus 400R, and then minus 20R squared. So now here is the formula that we're going to work with. Okay, so like I said, this problem and ones like this, the setup is a huge piece of the work to solve this. So let's go ahead and now perform our calculus steps. So we're going to have P prime of R. So we're going to take the derivative. That's going to be 200 minus 40R. We're going to set that equal to 0. So we get 40R equals 200. So R is 5. We're going to verify that this does produce a maximum. So pick a number smaller than 5, like 0, and we get a positive. Pick a number bigger than 5, like 10, we get a negative. So this does maximize profit. So now let's go back to the question. Find the price of each item that will produce the maximum profit. So we know that R is 5. This is the number of price reductions that they should use in order to maximize profit. So for our price, right, that was, actually let me color coordinate this a little bit. So this was the price that we established back up here. So that's what we're doing here. So price is 400 minus 10 times the number of reductions is 5. So 400 minus 50 is 350. And again, kind of like with the last one, if it was asking for the maximum profit, we would just do P of 5. So just plug 5 into this equation, and you would get 4,500. It also didn't ask for the quantity that makes this happen, but again, you could find that by just plugging in 5 into here, so that gives us 30. Right. So now our conclusive statement. So the maximum profit of $4,500 per week occurs at a price of $350 per item when they sell 30 items. Again, what the question was really searching for was this price per item. So that's the key takeaway here. But again, if it had asked for any of those other things, we could also have determined those as well. All right, let's take a look at one more example with a diagram ready to go. A rectangular box with an open top is to be made from a 10-inch by 16-inch piece of cardboard by removing small squares of equal size from the corners and folding up the remaining flaps. What should be the size of the squares cut from the corners so that the box will have the largest possible volume? Okay, so you can see down here, I've got my my big piece of cardboard, and we're going to create a rectangular box by cutting out these little squares out of the corners. We are trying to figure out how big those corners should be, how big of cuts we should make in order to maximize the volume of the box. Okay, so we know that the whole thing is 10 by 16. So like this whole length here, this whole length here would be like 10 inches. And then like this whole length here would be 16 inches. We know that the cuts are going to be squares. So it's asking what should be the size of the squares. That's what it's asking for. So that we will have the largest possible volume. So we're trying to get volume of the box once it has been folded up. And so we're looking at these lengths here. In terms of the box, we'll call this one the length and this one the width. For the cuts, once you cut the box, if you can picture taking each of these sides and like folding it up, and same thing, folding up all the sides like this, these actually form the height of the box. So that's these right here. So I'm going to call these H. Each of those little cuts that is being made. All right. Now, we need equations that relate the variables to each other, and we need an equation to maximize. The equation to maximize we can get very quickly. It's volume, which is going to be length times width times height, because it's a rectangular box. For the other equations, we need L and W. We need to get rid of them so that we can find H. We know one side is 10, one side is 16, and we can actually equate these. So I know that for the 16, for example, these three pieces would add together to give 16. That's going to be an H, and an L. Right? So we know that 2h plus L is 16. And on this side, we know that this length, which is W, plus 2h's gives us 10. So 2h plus W is 10. We can solve this. L is 16 minus 2h. W is 10 minus 2h. And now both of these can go in here. So we're going to have V equals 16 minus 2h times 10 minus 2h times h. So V of h will be, if you multiply all of this out, so FOIL it and then distribute that extra h, we get 160h minus 52h squared plus 4h cubed. And now we can work with this. So we're going to take V prime. We get 160 minus 104h plus 12h squared. We set that equal to 0. Now we have to do a little bit of algebra, but we can divide everything here by 4. So that would give us 40 minus 26h minus 3h squared equals 0. Plus 3h squared. This set of terms is factorable. We get 3h minus 20 times h minus 2. So we're going to get two values. This one, you add the 20, divide the 3. We get h is 20 over 3. This one gives us h equals 2. But if we're trying to decide which of the values it should be, there's an important thing to take note of. This value of 20 over 3, if you do the division, this is approximately 6.67, right? 6 2/3 is that value. That means that the cut that we would make would be almost 7 inches wide. And if you go back up here, if I'm taking this cut and I'm going to make it over 7 inches, so this is 10, so I'm going to make a cut like right here, and that's going to somehow be, it would have to go down like that. But then I need to make a cut from this side, and I need to go 7 inches that way. And I can't, because that part has already been removed from the box. So the cuts are too wide. We can't make a cut more than 5, right? If you cut it at 5, you perfectly split it in half. So even that realistically is not practical. But we certainly cannot cut anything bigger than that. So we have to note that h has to be between 0 and 5, or else there's no box. Okay, so even though algebraically this value is valid, in context, it's not going to work. So we can go ahead and just eliminate that as a possibility. So we're just going to work with h equals 2 here. So if we go to verify, we can set up our number line at 2, pick values less, so we'll be between 0 and 5 here. So if I pick like 1, then that's going to be 40 3 minus 26, that's a positive. If I pick something like 3, it ends up flipping it to negative. So it is a maximum. Okay, it does give us a maximum volume. And the H value is 2. What did the question want? The size of the squares, right? That's all it asked for. So we can go ahead and conclude to maximize volume, cut out 2-inch by 2-inch squares. So that will give us the largest possible volume for the box by taking these cuts to be 2 inches wide each. All right, and that brings us to the end of section 3.3. When we come back in section 4, we're going to be looking at some additional applications, particularly in the realm of business and economics. We're going to use more derivative rules and properties, and then we will be finishing up this topic. So I will talk with you all in the next one.